Alright guys, let's look at some operations on complex numbers. So what we're doing here is we got a complex number in polar form, a second complex number in polar form, and we're seeing that how do I divide and multiply and divide these. Literally I can multiply the magnitudes, alright, and then add the arguments. So I'm adding the argument from the cosine part of the first one plus the cosine part of the second one, the sine part of the first, sine part of the second one within the sine function. So we're just adding these angles together. So what does that mean? That means that visually, so here's a little visual of how do I multiply complex numbers. So this, let me add in a y-axis. So that would be x equals 0, and let's label that thing. This is the imaginary axis. This is the x-axis, the real axis. So if you look right here, it's hard to see it right now, but I've got a couple of numbers. All right, so there's they're on the 1 radius, and sorry, that's the 2 radius, and then I'm gonna put the blue and the red there together on the 2 radius. And if you look, this is their product. The product is this imaginary multiplication. So these two numbers, 2 and 2, are multiplied together, and I get 4. So 2 times 2 is 4. There is no rotation. But when I start to rotate the numbers, so there's 30, and let's take this one out. Now notice the purple is their product. So when I rotate it out, let me move this down a little so you can see, 30 and 30 is 60. So the two angles have been added together, which is what the notation says, and we've multiplied the products together. Okay, so if I went out all the way to the 3 one, alright, for that one, that's 6. 2 times 3 is 6. So we're multiplying the magnitudes and we're adding the angles. So if I add, there is 15 and 30. When I add those together, I get 45. Alright, so what happens when we combine two complex numbers via multiplication? What is our notation saying? It ends up being rotation. We rotate by combining the angles together. So starting with this one, if I multiply by another one, I rotate. The product will be the rotation of this angle plus this much more, whatever this other angle is, and that's what I'll get as the product of these two. It ends up being stretching or shrinking if the magnitude of one of these is less than 1, and rotation. And then likewise, since division is the inverse of multiplication, when we divide, we subtract the angles and we divide the magnitudes. Alright, so this we got two complex numbers. 3 is our argument here, our magnitude here. 5 pi over 6 is our argument. And then 2, so our product is going to have 6. And then we're going to add these two together. Now, the cosine of 5 pi over 6 plus 2 pi over 3, I'm going to get a common denominator, alright, which is 6. Alright, and if I did that, I'd have a 4 pi over 6, and that's going to give me 9 pi over 6. And 9 pi over 6 reduces to 3 pi over 2. They both have a common 3, so we could reduce the fraction. Always reduce your fractions with any of these problems you're working. Alright, then we just evaluate cosine of 3 pi over 2. If you look on your unit circle, the x-coordinate there is 0. The sine of 3 pi over 2 is negative 1. So 6 times 0 is 0, minus 6 times negative 1, or plus 6 times negative 1 is negative 6. And then there's the I. So negative 6i is what the product of those two numbers would be. Alright, let's look at one with division. Okay, so if I have these two and I want to divide, Remember, I'm going to divide this by this. I'll get a 3, and then I subtract the angles. So I'm going to get 6 divided by 2 is 3. 117 minus 72 is going to be a 45. So we get 3 cosine 45, I sine 45. These are special angles, so let's evaluate it further. Cosine of 45 is square root of 3 over 2 times 3 will be, cosine of 45 is square root of 2 over 2 times 3 is 3 square root of 2 over 2, or you can write that equivalently as 3 divided by the square root of 2. Recall 1 divided by the square root of 2 is the square root of 2 over 2. So this is an equivalent form of 3 square root of 2 over 2. 3 square root of 2 over 2. It's perfectly fine to write it either way. We talked about that, how our scientific calculators and things like that have kind of eliminated the need to rationalize denominators. So there it is with an irrational denominator. Alright, now we've got these 2e to the I pi over 3, 3e to the I pi, 5 pi over 6. This is Euler's formula. Euler's formula says e to the I times some angle. Is that polar form of that, like we've been seeing? It's cosine of the angle plus I sine of the angle. So this is just another way to write the polar form of an angle. So notice EI theta, that's EI theta. So all we're doing is replacing theta with pi over 3, and then for this one replacing theta with 5 pi over 6, 5 pi over 6. So this is just like our Z1, Z2 thing that we saw before. These are just polar forms of numbers. So first of all, how am I going to multiply these? I'm going to multiply the numbers and then add the angles, just like before. So it's the same concept. It's just this is another way to write these polar forms of numbers, is to write in this exponential form. And it's again called the Euler formula is what relates these two. So how would I do it? I would do what we did before, multiply the magnitudes. So 2 times 3 is 6, add the angles, or add the arguments. So this is 2 pi over 6, 2 pi plus 5 pi is 7 pi over 6. So that's what they would be. And then this is how far I rotate with a magnitude of 2. This is how far I rotate with a magnitude of 3. And this is how far I rotate with a magnitude of 6 when I apply them together. Alright, so there's my magnitude of 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6. Alright, and then there's the angles. Pi over 3, 5 pi over 6. Looks like that should be a little bit further down. Anyway, and then 7 pi over 6. So anyway, that's the idea. We rotate by these angles and we stretch to these magnitudes, and that's the Euler's formula is a way to write that in a nice, more compact notation.